Hello students, today we are going to start with module number 4 of the syllabus. Name of the module is Backtracking and Branch and Bound. In previous two module number 2 we discussed dynamic programming approach. In module number 3 we discussed greedy approach. Let us quickly revise important points or important features of these two approaches and then we shall start with backtracking approach. In case of greedy approach, we discussed three important points. Those were, first one was feasible solution or feasibility. Second point was locally optimal. And the third point was irrevocable. Now, I would like to discuss this irrevocable property once again because this is exactly opposite to the backtracking approach. In irrevocable property, what it says, while solving the problem, we are expected to take certain number of steps. At each step, we have to make some choice or take some decision. In case of greedy approach, once you have taken a decision and after going in the subsequent step, if you realize that whatever decision you have taken in a previous stage or previous step is wrong, then you cannot go back to the previous stage and change your decision. That is what irrevocable property. Now this is exactly opposite to the backtracking approach. I'll come back to this particular topic once again. One more topic we discussed, that was dynamic programming approach under module number 2. Dynamic programming approach has got two important points. One was optimal substructure property and the second was memoization. So using these two approaches we have solved certain number of problems. Now with the help of backtracking and branch and bound approach we will be solving few more problems. Now let us understand what is backtracking. Backtracking approach is generally used if you are trying to find out all possible solutions for the given problem. When it comes to solving a problem, we are expected to take certain number of steps and in each step we need to take certain decision or we have to make certain choices. So backtracking approach is useful if the series of decision needs to be taken in the process of problem solving. Second point says backtracking is considered to be faster than the brute force method. So we are going to discuss this point with the help of one example. Under backtracking, the problems are going to be a constraint satisfaction problem, and for backtracking algorithm, the state space tree will be generated to find out all possible solutions for the given problem. Now let us understand difference between backtracking and brute force approach. Before starting with the example, I would like to tell you very important point that brute force approach is a very simple and systematic approach where you try to find out all the possible solutions without applying much logic. The backtracking is considered to be an extended version of brute force method. Now let us understand this particular example and I'll draw state space tree for the given example using brute force approach and then I'll change the same state space tree using backtracking approach. Now here you are asked to set password for given application and length of the password should be 3. Here we have also given the characters, that is small a, small b, small c. Here we have to use all the 3 characters in order to generate the password. So with these 3 characters, there are 3 factorial ways to generate the password, which I have already mentioned over here: ABC, ACB, BAC, BCA, CAB and CBA. So there are total 6 passwords can be generated with the help of these three letters. Now if I have to generate state space tree using brute force method, then my state space tree would be this is the starting node. Now first character I can select any one of this. So let's say I have selected A. Then the next character, for selecting next character, I have choice of B or C. So I'll select B or C. I have already selected A. Now second character was B, and the third I can select is definitely C. Suppose I have selected A and the second character is C, then I am left with a choice of B. Again, if I am choosing first character as B, then I am left with two choices, that is A and C. If my first character is B, second is A, then definitely third is going to be C. If it is B, C, then definitely it is going to be A. Similarly, if I am choosing first character as C, then there will be two choices, that is A and B. If it is C, A, then the last is going to be B. If it is C, B, then it is going to be A. So this is how state space tree will be generated using brute force approach. Now here all the 6 solutions are shown in the state space tree. As I told you, backtracking is a extended version of brute force method. So in case of backtracking, we have given certain constraint. So now I'll add one constraint to this problem. The constraint is the middle character should be B. What is the constraint? That middle character should be B. So I have to consider that whatever solutions I am generating, the middle character or whatever password I am generating, middle character should be B. So now let us again go through this state space tree. I'll go by depth first search. So I'll start from the root node. My first character is A. Now middle character is B. Okay, so constraint is satisfied and I'm not concerned about what is the last character, but middle character should be B and all the 3 characters should be present in the password. So first branch is the right solution. Now let us check for the second. So first character is A. Now second character is C, and what is the constraint? Middle character should be B. So as middle character is different from B, so here itself I am going to cut this particular node and I won't extend it further. Similarly, let us check for the second one. Now here starting character is B, middle character should be B, but it is not there, so again this is wrong. Second, again this is wrong. So whenever constraint is not satisfied, we are here itself the node gets end and you are not going to extend it further. Similarly here itself it will get close or end and you are not going to extend it further. Now let us check for C, A, B. Again this is not a correct solution, so here it will get ends and won't be extended over here, and the last one C, B, A. So again the middle character is B according to constraint, so this is the right solution. So we have 2 right solution. First one is A, ABC and the last one, that is CBA. So when some constraint is put, then the state space generation would be different than the brute force approach. So in case of brute force approach, we do not check any constraint and we find all the possible solution, whereas backtracking is an extended version of brute force where certain constraints are imposed and those constraints needs to be verified while generating a state space tree. Now when you generate a state space tree and if we found out that any constraint is not satisfied, then at that point itself you are going to end that particular node and no need to extend it further. And by doing this, you are saving the time as well as space. So I hope you are clear with the solution. Now let us understand this backtracking with a simple example. So backtracking in case of backtracking, state space tree is generated with the help of DFS, or it is similar to DFS, where you are going to start with root node A, then first left node, that is B, then again you will go to the depth or down towards C, then you will again go back to B, then you will visit D, E, again you have to come back to the previous node D, B, and then you will go to the A. Similarly, you are going to visit remaining branches. So in case of backtracking, the state space tree will be generated similar to the generation or similar to the working of DFS. Now we are going to start with the first problem under this module, and the problem is graph coloring problem, which is also called as a vertex coloring problem. Now let us understand what is this problem. So here you will be given a graph which is denoted as capital G, and you will be given certain number of colors and they are denoted as small m. Now the objective is to color all the vertices of the graph in such a way that no two adjacent vertices should have same color. Let us understand this with example. So here is the example. Here two graphs are shown. This particular graph, second graph, this is called as a Peterson graph. Here you can see that all the vertices have given some color and none of the adjacent vertices have same color. For example, if I consider this vertex which is given red color, now adjacent is given green, this adjacent is given white, and this adjacent is given green. So this is how you are going to color all the vertices by making sure that none of the adjacent vertices will have same color. Here we have considered one more diagram where we have four vertices A, B, C, D, and we have given two colors, green and blue. So here with these two colors, all the vertices have been given a color without violating the constraint, and here the constraint is adjacent nodes should not have same color.